Welcome to This Explainer. Have you ever wondered if you could take a mathematical equation, just an incredibly complex, downright chaotic stream of numbers, and somehow run it through a medical CT scan? What do you think you'd see? Would it just be random static, or would you uncover the hidden pulsing skeleton of the universe's logic? Well, today, we are diving into a newly verified, totally mind-bending experiment known as the 2048-digit pi fold. And I'll tell you right now, it is a real game changer. It challenges literally everything we think we know about how information is processed, compressed, and potentially how it can be completely resurrected from the dead.
So let's dive right in. The ultimate mystery of cryptography, and really physics as a whole, boils down to one massive question. Is data ever truly lost? Think about it. When you mash numbers together, subtract them, and fold them over and over until they look like pure random noise, is the original information actually destroyed? Traditional math generally assumes that when numerical value collapses, the data is just gone forever. Poof. But what if it isn't? What if it's just hiding?
Here's our roadmap for today. First, we'll be folding pi's chaotic digits. Then, discovering the parity shadow. After that, we'll hit the 448 Nyquist pin, move into the level 512 freshman's dream, and finally wrap up by reversing time with tomography. Let's get started.
Number 1. Folding pi's chaotic digits.
Okay, so to really grasp the grand, universal application of this, we first need to ground ourselves in the exact base experiment the researchers ran. They started with the first 2,048 decimal digits of the transcendental number pi, and then they applied a super simple but highly destructive rule called the adjacent difference fold. Basically, you take the absolute difference between two adjacent numbers to create the next number directly beneath it, and you just do this over and over again, layer by layer. Because you're left with one less number every single time you step down, it naturally forms this massive, shrinking triangle, a cone of data, progressing from level 0 all the way down to a single point at level 2047. Honestly, it acts like a giant chaotic meat grinder for numbers.
Now, the data from this reveals a really dramatic contrast. By just level 8 of this fold, the absolute amplitude, meaning the total numerical value of those pi digits, has already collapsed by an astonishing 88.3%. The raw numbers are dying off rapidly. But here's the wild part. While those numbers are dying, the shape survival, the physical number of active, non-zero cells, has only dropped by 0.6%. So the numerical value is being aggressively destroyed, but the topological shape of the data, it's stubbornly surviving. And that right there is our first major clue.
Which brings us to section 2, discovering the parity shadow.
Okay, so if the shape is surviving, how do we actually see it through all those chaotic decimal values? We essentially need a mathematical X-ray. The brilliant clue the researchers used relies on a fundamental modulus equivalence theorem. Instead of getting bogged down in the messy numbers, the 7s, the 4s, the 9s, what if we project this entire massive cone through a simple modulo 2 filter? Put simply, what if we just ask one binary question for every single cell? Is this number even or is it odd?
When you project the chaotic decimal differences of pi into modulo 2, the absolute distance perfectly maps out to binary addition without carry. It degenerates precisely into a logical exclusive or XOR operator. It is almost spooky. Suddenly, that chaotic decimal collapse perfectly morphs into a highly structured binary grid known as Rule 90. And to be clear, this isn't just some approximation. Actually, scratch that. The source emphasizes it is absolutely not a toy model. Cell-by-cell verification proves this binary lattice is the exact unadulterated topological skeleton of the original decimal collapse. The chaos we saw earlier, it was just an illusion, hiding this absolutely perfect geometry.
Moving right along to section 3, the 448 Nyquist Pin.
So this geometry allows us to see structure right where we previously just saw static noise. As this binary mass drops down through the levels of our data cone, it aligns at very specific depths to trigger some profound topological events. We are looking for what the researchers call lock points. These are exact evolutionary coordinates where the pseudo-randomness of the fold finally reveals itself as a highly structured, long-range algebraic sampling. And our first major lock point hits at depth 448.
Let's break down exactly what's happening at level 448. In binary, 448 is made up of 256 plus 128 plus 64. That means it has exactly 3 active bits. Because of how the algebraic geometry shakes out, this mathematically forces the system to sample exactly 8 distinct parity points spaced precisely by 64 bits. It's essentially acting as an 8-point parity probe on a 64 grid. And the measurements confirm this flawlessly. At level 448, there are exactly 1,600 total cells, and exactly 800 of them are active ones. It's a perfect half-density lock with absolutely zero residual error. They call this the Nyquist Pin because it's the precise moment the apparent randomness of pi resolves into rigorous, visible sampled structure.
Now, Section 4, Level 512, Freshman's Dream.
As we plunge even deeper into the data cone, the mathematical mask shifts completely. Level 512 is entirely magical because 512 is a pure power of 2. When you're operating in this binary parity shadow, which mathematicians call a Galois field of 2, a pure power of 2 triggers this beautiful algebraic shortcut named the freshman's dream. This identity dictates that the incredibly complex binomial theorem just dramatically simplifies. The massive, multi-point grid sampling we just saw at level 448 suddenly collapses down into a starkly simple, 2-point long-range sample.
So, what does that mean in practice for us? Well, at depth 512, the system is simply taking one bit and comparing it to another bit exactly 512 positions away. It's a direct 512 lag parity comparison reading long-range separation. And once again, the empirical data from our 2048-digit pi run confirms this. Out of the 1,536 bits compared to their shifted copies, there are exactly 764 ones and 772 zeros. That is an almost completely perfect balance. Level 512 is essentially acting as a macroscopic verification of the entire sequence's internal wave structure. It's like the math is literally talking back to us, showing off its hidden internal symmetry.
And finally, Section 5, Reversing Time with Tomography. So we have these amazing geometric probes locked into the math. But what do we actually do with them? Well, this is where the real magic happens. We can treat these lock points like that 448 Nyquist pin and the 512 freshman's dream, just like X-ray slices from a medical CT scanner. In discrete tomography, you reconstruct the inside of an object strictly from its orthogonal projections. The researchers realized that by gathering all these different geometric probes, literally stacking the deep X-ray slices right on top of the shallower ones, they could build a full, multiscale tomography system. By using massive systems of equations to systematically track the physical footprints backward, they effectively reconstructed the original 2048-digit starting seed address strictly from that surviving shape channel.
Which brings us to the profound philosophy at the heart of this entire framework. The value of the data, those specific, messy, decimal numbers, dies. It is completely lost in the forward collapse. But the shape of the data, that beautiful binary parity skeleton, survives. And because it survives, and because we now know how to read the lock points, the entire process is entirely reversible. Data isn't actually destroyed, it just loses its location.
I want to leave you with this exact, incredibly powerful quote straight from the source material. Forward collapse hides information by losing address. Reverse recovery restores address by reading shape. We used to think these complex mathematical folds were random destructive black boxes, but they absolutely aren't. They are highly structured, entirely reversible geometric machines. So, the next time you think a piece of data is permanently lost or completely destroyed in the chaos, you really have to ask yourself, are you just staring at the value when you should be looking for the shape?